Welcome back. In the last lecture we discussed about the motivation for using finite volume time domain method, and we also gave you background on the mathematical formulation which comes from the computational fluid dynamics. Obviously we don't understand the physical meaning of those formulation, and this is what we will be discussing this lecture, and then we will discuss a little bit more about the discretization itself. So let's begin with the form of the equation which I gave you before. So this is basically a one-dimensional flow equation which I said. So let's simplify this equation even further. Let's say that we are having a form where we are using, let's say, d of u of t, and then we say that there is a which will be discussed in this lecture, and then say du of dx. So this is a very simple form. If you compare this with the equation that we have here, this is nothing but we say that a equal to 1 in this case, and df by dx is nothing but du by dx. So this particular form is the more general form, and we are going to use this general form to understand. Like I said, in our earlier case we had du by dt plus a, we said it's 1, and it's df by dx. So you can see the similarity between these two equations. So we will be starting to work with this more general equation so as to get you a better understanding of what do I mean by this a, what is the significance of this a, what is the significance of the entire equation. So we say that this equation is of the form hyperbolic if a is a m by m matrix and a is diagonalizable and a has real eigen values. So we know that from the basic linear algebra, a matrix, a square matrix that is diagonalizable will have certain eigenvalues, and in the case of this form we call this equation as hyperbolic if a is an m by m matrix and it is diagonalizable and it has real eigenvalues. Let's say the eigenvalues are represented by, so lambda 1, lambda 2, lambda 3, so on until lambda m. Since it's a m by m matrix, we will have m eigenvalues. So if this particular eigenvalues are all having certain properties, the property is if they are all real and they are all in a way that they could be same, or they could have certain properties, they can go in a increasing order, or they could be all same. So but if they are all real, we call them as hyperbolic. But if these eigenvalues are all real but distinct, in other words, lambda 1, see lambda 2, lambda 3 until lambda m, so they are all different, so there is no equality sign here, and they are all distinct. So if they are distinct and real, they are called as strictly hyperbolic. So we know from the linear algebra that once we are talking about, let us say, eigenvalues, there is also corresponding eigenvectors, and these eigenvectors are, let us say, are represented by R, the letter R, and they go from R1 to R2 until Rm, and these are all the eigen vectors. The word eigen comes from German, basically means characteristic. So when you say eigenvector, they are nothing but the characteristic vector, and eigenvalues are characteristic values. So when we say characteristic, the question comes, what do they characterize, right? So the relation between an eigenvalue and eigenvector is given by the relation which is A, the same matrix A which we saw before, R of P, which is the eigenvectors, is equal to the lambda, which is the eigenvalue of P, times Rp, and P goes from 1 to m. So this is the basic equation that defines the relationship between an eigenvalue and eigenvector for a given diagonalizable m by m matrix. So that being said, we wanted to know what is the structure. Let us say we talk about a particular matrix which is consisting of all the eigenvectors. R is equal to R1, R2, R3 until Rm. So this is nothing but a kind of a column vector which has all the individual columns represented by R different eigenvectors. So if we say that R is a column vector, and depending on whether we use them as a column vector or a row vector, we have to adapt the equation accordingly, but the idea is once you have the definition of the column vector, the eigenvalues and eigenvectors, we can have them written of the form which is basically R inverse of A is equal to capital lambda. So the equation here is the definition of the relationship between the eigen vector and the big lambda. So the big lambda is nothing but a diagonal matrix consisting of all the lambdas. So you can also see, we can write the same expression as A is equal to R capital lambda R inverse. So I am pre-multiplying or post-multiplying with accordingly the matrices, so I can get from here to here. So, and I told you that lambda, the capital lambda, is equal to, it's a big matrix, diagonal matrix, and it has various eigenvalues along the diagonal. So if this is clear, what we are going to do is we are going to find how we can use this particular form in the first equation what we had. Basically we are going to use the definition of A in this particular equation, and then we are going to find a way to decouple the equation into various terms. So what we are doing here is we are going to multiply the equation which we had before. I will write down the equation one more time. So which is du by dt, we have plus a du by dx is equal to 0. First of all, we can substitute for a using the value that we got in the earlier stage. So a is r big lambda r minus 1. So this I can put it already in this equation. So du by dt plus r capital lambda r minus 1 du by dx is equal to 0, and I can pre-multiply this equation using r minus 1. So I will get r minus 1 du by dt plus r minus 1 r lambda r minus 1 du by dx is equal to 0. So what I can say is, I can say I will define a new quantity which is nothing but a definition for simplifying this equation. Let us say I call it w is equal to r inverse u of x comma t. So what I am saying is, if I use this particular definition, I can basically simplify this part by putting w, and I can simplify this part putting w. This one will become 1 because it is r inverse times r, and then we will have only a term that is with lambda, capital lambda. So this equation will be looking like this. So what we will have is dw dt plus the individual lambdas. So we will have the bigger lambda times dw by dx is equal to 0. So what I have done is nothing but I have adjusted for, I have used this definition. So maybe I will use only w here, but then when I am doing the equation, you will see dw of p by dt plus lambda of p dw of x is equal to 0. So basically these are the individual components because this is a diagonal element. So when you multiply the diagonal element, what you will get is only the p component, and then you will get individual equations. With this understanding, we will describe how this particular form will be helpful for us to use in the Maxwell equation while we go into the next step. So as I said, right now what we have done is we have got an understanding of what is the meaning of advection equation in hyperbolic form. We said that this form will have eigenvalues, and if they are distinct, they are called as strictly hyperbolic, and we have also shown that this form can have certain meaning in terms of the propagation. So this we will see how it is reflecting in the case of Maxwell equation. So what we are going to do is, we are going to take a simple Maxwell equation and we are going to discuss how this whole thing is going to come into effect. So let us take a simple curl equation which is basically given by the Maxwell laws, which are dB by dt is equal to minus curl of E, and we will have dd by dt which is equal to curl of H. So this is the form we are going to use. Obviously we do not take any source terms, So we assume the source terms are 0. So this is the form that we will start using. So this form, for a simple case where material parameters are scalars, so that means D is equal to epsilon E and B is equal to mu H. Obviously these are all vector quantities. Epsilon is the permittivity and mu is the permeability, and we choose them to be constant. So accordingly this expression will be simplified for the case of simple Maxwell equation as E by dt is equal to 1 by epsilon the curl of H d H by dt is equal to minus 1 by mu the curl of E. This is a 3-dimensional equation. It has totally 6 components, but let us take a simple case where we are talking about E has only component along the y direction. And H, or let us take B, has only component along the z direction 0 0 bz x comma t. The reason I am using B here is to make a connection between this particular form and the eigenvalues and the A matrix that we learned before. So with this we know that we can model the equation accordingly. So what we are going to talk about is we have case where the values are changing. Let's say this is the z axis and this is the x axis, this is the y axis and then z axis, and what we are talking about is E field is only along the y direction and it is going along x, and we have the B field which has only component along the z direction and it is also travelling along the so this is along the plane of xz. So this is in the plane of x z plane, and this one is in the plane of x y. So for this simple equation what we get is we get a form where we can write E y d by dt plus 1 by epsilon mu d b z by dx is equal to 0, the b having only component along z direction and it is the partial derivative with respect to x, and the b component will have a similar partially differential equation which is written as d bz by dt plus E, so I will put 1 partial derivative of E y with respect to dx equal to 0. So we have a coefficient equal to 1, but here we have a coefficient 1 by epsilon mu. I have specifically taken this form so as to get the matrix formulation where we see that this is very similar to the equation what we had before, which is basically du by dt A du by dx equal to 0. So what we have is a matrix form which is A, and the components of the A are given by these components here. And for this particular case, what we will have is A is defined by a M by M matrix. Since it's a two-dimensional form, we will have a 2 by 2 matrix whose values are written as follows. And you can verify that this A can be diagonalized, and it will have eigenvalues which are given by lambda p, in this case lambda 1 is equal to minus c, and lambda 2 is equal to plus c. Since lambda 1 and lambda 2 they are distinct, these are a representation for a strictly hyperbolic system. And obviously there is a connection between the C and the components here. So C is nothing but 1 over square root of epsilon mu. So this is the characteristic velocity in which the wave propagates. As I said, eigenvalues are nothing but characteristic values, and these values are defining the certain properties of the particular hyperbolic form. In this case we see that these are the two directions in which the wave propagates. One is a left propagating, the other one is a right propagating wave. And obviously when we talk about a free space, we will have C is equal to 1 over square root of epsilon naught mu naught. This is the case for a free space or vacuum. We have seen now how the hyperbolic form is useful, because you might wonder why that we start talking about hyperbolic form or eigenvalues or eigenvectors when we can directly go and model the entire equation. It's always better to get a physical feeling for the kind of equation we are talking about. So in the case of the Maxwell equation, it's a hyperbolic equation, and these equations will have real and distinct eigenvalues, and these values are nothing but the propagation velocity. In the free space it is the free space speed of light. And so with this understanding, we will look in the next module about the discretization itself. How are we going to discretize it? What are the benefits of doing that? What are the values that we are storing? And we will also pay attention to the actual Maxwell equation for numerical solution. Thank you.